Hello everyone. Uh, this week we are going to learn about an analytical method that enables us to solve circuits in an easier way, which is the Laplace transform. This allows us to basically convert integral differential equations into linear equations, which are easier to solve. So let us get started. Throughout the course, we will learn about the definition of the Laplace transform. We will learn about the step function and also explore impulse function. We will learn about functional and operational transforms as well as applying the Laplace transform, which allows us to make a transition from time domain to frequency domain. And we will learn about inverse transforms, which help us to come back to the time domain. Then we will learn about the concept of poles and zeros for transform function, and we will talk about the initial and final value theorems. All right, let's hit the road. Um, why do we need this technique? First of all, historically, when people were dealing with integral differential equations, they had limited computational capacity. Because of that, all these methods are basically developed to be able to obtain easier analytical solutions, or to obtain these analytical solutions using fewer, steps. Uh, so, in the context of electrical engineering, uh, we face circuits with lots of nodes and meshes. However, as human beings, our capacity to solve complicated circuits is limited. But as we have seen before, when you have um, when we use the tools of linear algebra, it's possible to solve uh, much more complex equations, especially the number of linear equations doesn't really matter actually, as long as you can represent them as in the matrix form and use the Gauss-Jordan elimination, for instance. You can basically solve n equations. So we are good at solving linear equation systems. And thanks to the existence of Laplace transform, it's possible to convert time domain differential equations into frequency domain linear equations. Basically, the importance of the Laplace transform comes from this fact. It makes life very easy. In addition, it makes circuits solvable basically, even by hand. We would like to, most of the time, we are interested in the transient behavior of circuits. There are equations that define the time domain behavior, and most of the time, these are differential equations. What happens when we turn on the switch? What happens when we apply the power? This is a very common question, and we use circuit simulators such as SPICE to estimate this behavior. However, in analytical terms, in order to estimate what will happen when you turn on a switch, we do it by using the traditional circuit analysis methods such as the KCL and KVL, and they yield integral differential equations of order of like this one third order, the first order, second order, or third order. I mean, you will be dealing with time domain equations which are hard to solve. What we would like to determine, we also would like to determine the transient response of circuits whose signal sources may vary. For instance, what happens if I apply a sinusoidal signal to the inputs of the circuit? What kind of response will I get? As we have learned in the sinusoidal steady state, solutions or topic, for certain kinds of signals, it's possible to solve these time domain integral differential equations. But for for any kind of signal, we would like to learn or know what happens. And basically, most signals that we have worked with were simply DC level jumps, like the step function, which mimic the behavior of a switching on or a switching off event. But in more complicated situations, it becomes very hard to solve the circuit equations in time domain. And we can use Laplace transform to introduce the concept of the transfer function, which is very important in electrical engineering because it constitutes a new paradigm or a new perspective for engineers to handle complex system level problems. So we use this as a tool for analyzing the steady state sinusoidal response of a circuit when the frequency of the sinusoidal source is varying. And we would like to relate the time domain behavior of a circuit to its frequency domain behavior in a systematic fashion. And because of this rationale, Laplace transform helps us to achieve and achieve lots of possibilities like the things that I have mentioned. So let us continue and learn more about the details of this fascinating transform. Okay. Uh, how do we define the Laplace transform? Basically, here, as you can see, we have a function fs which represents the Laplace transform of a function ft. Okay, when you have a function ft in time domain, its corresponding transform in the Laplace domain or the frequency domain will be represented by a capital F and S. S represents the complex frequency. In the future, when you learn about signals and systems courses, when you learn about the Fourier transform, you will see that S equals to j omega. But for the time being, let us not complicate things and forget about it. And the LFT is the operator for the time domain to frequency domain transform. That is, we use the L for representing the Laplace transform, operational Laplace transform. And the meat is here, like the Laplace transform is defined as an integral from time equals 0 to infinity. And we simply multiply the function that needs to be transformed with e to the minus st dt. When we solve this integral, we will obtain a function in terms of s. But when we are taking the integral, the variable that we will be handling will be with respect to t. So the s will be something like a constant to us. And the reason that we call the Laplace transform a frequency domain representation comes from the fact that we know that the t represents time, but the integral should be like unitless in such a way that in order to counterbalance, the s has to be the reciprocal of time, and the reciprocal of time means the frequency. So this is why this transform moves us from time domain to frequency domain. So basically, Laplace transform transforms the problem from time domain to frequency domain, as we can see here. After obtaining the frequency domain expression for the unknown, we can always go back. So we can go back into time domain again, uh, which would give us the solution of uh, the original integral differential equations. So we will learn about how this is done. Uh, so as I mentioned before, this Laplace transform basically helps us to uh, transform the a set of integral differential equations from time domain to a set of algebraic linear equation system in frequency domain, which is pretty solvable using the basic tools of um, linear algebra. Well, as you can see here, the upper limit of the integral is infinite, so it's an improper integral basically. So it means that some functions may not have, some functions may not converge. So the integral may not converge basically, not the functions, but however, those functions are not, related to us. That is, in the functions that we will be dealing with are the functions which have Laplace transform. So it's not going to be a problem from engineering point of view, but from mathematical point of view, it could be something that bugs people. So as I mentioned, like when we see that infinite at the boundaries of the integral, we immediately, ask ourselves the question: Is it, does the integral converge? But we are only, interested in the functions that have the Laplace transforms. Functions such as the t to the t or e to the t square kind of functions are typically divergent, especially with the integral, within the integral. However, we won't be encountering that kind of signals in the work that we will be dealing with. So it's not that important. And the lower limit is zero. So basically, the Laplace transform ignores the ft for negative values of t. So everything starts with at time equals to zero, or this is also referred as one-sided or unilateral Laplace transform. And we integrate the function from 0 minus. Basically, 0 plus and 0 minus notations indicate that we include the 0 in our integral. And in practical terms, the initial value basically sets the starting point for the function. And when we are using Laplace transform in circuit analysis, we use this. We use the initial conditions as a starting point for the function value at 0 minus. Here we need to define certain terms, such as the functional transform and the operational transform. A functional transform is the Laplace transform of a specific function, such as the sine omega t, t, or e to the minus at, and so on. An operational transform is more general. It's a general mathematical property of the Laplace transform. So it's about finding the transform of derivative of ft. Okay. So we are basically introducing the basis for the Laplace transform and making some definitions to make it more clear. So let's go with the next slide. One of the functions that we have learned so far that we encounter in electrical circuits is the step function, which represents a sudden change of current or voltage in a circuit. We use this function to model the transient or the time domain behavior. So the step function is defined as a function with some discontinuity. As you can see, there's a jump at 0, and it has an amplitude of k, and k times ut. Basically, unit step function is the ut, and the step function is a more generalized term, which has some non, one amplitude, that is k times u t basically. So the function is defined as 0 for time smaller than 0, and for time greater than 0, the step function is defined as a constant value, which is the k. Okay, this is something like when you in a DC circuit, when you turn on a switch, the behavior is like this. When you connect a battery, this is what happens. Like you suddenly approach 5 volts or 12 volts to a circuit, and the circuit starts to operate. So step function is very useful in such cases because complicated, events can also be represented with the step function. And now the problem is step function is not well defined at t equals 0. There is a discontinuity here. And in situations where we need to define the transition between from 0 minus to 0 plus, which means that like it's very close to 0 but not 0 from the left hand side and the right hand side, we can assume that it's linear. So it has a ramp kind of behavior, as you can see here. Okay. This trick allows us to define or mathematically help us to solve problems. So with a finite, slope line, a transition, a softer transition can be defined to help us. So it passes through the midpoint of the amplitude at 0.5 k, as you can see. So we can define when the t equals 0, ku0 should be 0.5 k. So this is a definition that saves the day when we are dealing with these functions in the mathematical domain, when we are doing algebra with them. As every function, you can change the amplitude of the signal by multiplying with different k's. So you have degrees of freedom in the y-axis or ft axis. You can also shift this function in time to the left or to the right by adding t, by making a substitution, variable substitution into t. So it's pretty, elastic for us. It can be positioned anywhere in time versus amplitude axes. Now, the discontinuity since it's flexible and it can be shifted in time, the discontinuity may occur at some time other than t equals to 0. So as I mentioned, we can simply shift this function. For instance, if the step is occurring at t equals a, we can simply define it as q t minus a. So I just substituted t minus a for a positive a within the right hand shift. So we can define this using the basic step function. So for instance, for this particular case, I can define ku t minus a equals to 0 for t smaller than equals to a, or kut minus a equals to k for t greater than a. Here, if the a is greater than 0, the step occurs to the right of the origin. And if a is smaller than 0, depending on the sign of the 0, so a, the step can occur to the left or to the right of the origin, obviously. And typically in this case, if we look at this case, a step function equal to k for t smaller than equal to a can be written as ku a minus t. Okay, so here, as you can see, this can be represented by ku a minus t equals k. So in any case, it's possible to use combinations of these functions to write down finite pulses as well. we can write a pulse with a finite duration, finite non-zero duration, using the addition or subtraction of the basic step functions as well. So it's very handy in more complicated situations or signals, because you can simplify, or you can divide and conquer the problem using the basic step function. So the impulse function is something that's interesting, because we can encounter functions with a discontinuity, or a jump, or sudden change at the origin, or at any point basically. But we know that from basic algebra that it's not possible to take derivative, because derivative at that point, like this, think about this peak point at epsilon, it's not defined. You cannot find the slope here by taking using the traditional algebra. But we can use the impulse function to help us. Um, an impulse is basically the concept of the impulse function, basically something that enables us to define derivative at this discontinuity point, to fill the gap in such a way that we can simply mathematically write it. So the impulse is a signal with an infinite amplitude and zero duration. Now, this is um, fantastic, because in real world, the pulses that we encounter in real life will have some finite amplitude, and they will have also a finite duration. However, from theory point of view, an impulse is typically defined as a signal which has an infinite amplitude and is zero duration. Now, this really forces the math a lot. So we define basically a Dirac delta function to represent the impulse function, which is an extended function to help us getting rid of this discontinuity. Uh, okay, so in real world, we encounter impulsive voltages and currents. So we need these functions to be able to handle or predict the behavior of circuits, especially switching operations generate these spurious, impulses, or by, intention you generate them. To define the derivative of a function at a discontinuity, we need to think that the function varies linearly across the discontinuity. So, as you can see here in the, in this example, the function will have some, monotonic, change, and then this sudden thing, switching or undefined discontinuity point occurs. When we differentiate the function, the derivative between the minus epsilon and the plus epsilon is taken as constant at a value of 1 over 2 epsilon. And for time greater than, larger or greater than the, epsilon, we are going to take the derivative as, for instance, in this particular example, as minus a times e to the minus a t minus epsilon. So if we look as the epsilon approaches zero, the value of the derivative between the plus minus epsilon will approach infinity. So the duration of this large value is also will approximate to zero. So the pulse will be getting taller and taller as it gets thinner and thinner. This is why at the very boundary, we believe that, we think that the impulse function will have infinite amplitude with zero duration as we tune the epsilon, this infinitesimally small number, when we take it to 0. And typically the area is taken as unity, and as the epsilon approaches to 0, we say that the function between plus minus epsilon approaches the unit impulse function denoted by these, delta. This is basically a generalized function, delta Dirac function. So if the area below the impulse function is other than unity, then it's called as k delta function, which means that it will have an amplitude of k. So the area under the pulse will be the k. It's also referred as the amplitude, magnitude, or the strength of the impulse function as well. So we implement this impulse function from a variable parameter function whose parameter approaches 0. This is the epsilon basically. The variable parameter must exhibit the three characters. First of all, amplitude should approach to infinity, and the duration of the function should approach to 0, and the area under the variable parameter function should be constant when the parameter changes. So if these three conditions are available, then we can use this function in our circuit analysis approach. Okay. So if you look at the by definition, if we look at the function and its derivative, since I have a linear portion here, its derivative will be constant, as you can see, and between minus epsilon and the epsilon, I will have a constant, 1/2 epsilon value. Since the duration, as the epsilon approaches this, 0 from both sides, 1/2 epsilon will be growing, and it will be hitting infinity. You can simply use your imagination on that. And so the derivative of the function at 0 becomes delta t in this case, as the epsilon goes to 0. All right, so we need to talk about an interesting property, which is called the shifting property. Okay, the function typically a function of ft, when you consider it as an continuous function, we can simply represent that function in terms of the Dirac delta functions. We can compose it or decompose it. You will learn those things in signals and systems courses, but you will learn about those concepts. But here, in the context of electrical engineering, or in the context of circuit theory, we know that we will be using it for being able to define a derivative at a discontinuity point. We know that the impulse function is defined as, the generalized impulse function is defined as an integral from minus infinity to infinity, k times delta t dt. And since the integral basically defines the area under the curve, you know that we are going to get k as delta t times dt. The integral will yield the 1, because it's the unit impulse function. Okay. So we can represent this by k times delta function, delta t, as you can see. And we can also shift it in time if we simply make a substitution to t. If we substitute t minus a, the impulse function will be shifted in time. Okay. And the shifting property is something different than shifting. Sounds similar, but they are completely different things. The shifting property basically represents an interesting relationship. Okay. First of all, uh, when we have an impulse function that sifts out everything except the value of ft at t equals a, the validity of this follows the fact that delta t minus a will be zero everywhere but except at the t equals a point. Okay, so the integral can be written in this case in such a way that the function, the value of the function at that particular point will represent the value of the integral. Okay, and we can use the shifting property of the impulse function to find its Laplace transform. That's one of the best uses. Like when you take the delta t and multiply it with e to the minus st and take the integral from 0 to infinity, you will get 1 basically. And the Laplace transform of the impulse function will be basically 1. If you have an amplitude of k, then it will be correspondingly accordingly scaled. All right, so as I mentioned here, like we are able to define the the delta t, the impulse function. It's a kind of a weird function, like when you compare it to your previous experience, but it's integrable as it's zero everywhere, but only at t equals a or at some particular point. And the value of the function at that point will be the value of the integral. So we can use this property to calculate the Laplace transform, okay, of it. And as you can see, I have just created an integral. I'm just applying the Laplace transform definition. Delta t is my ft and e to the minus st, and here as the t goes to 0, the e to the minus st will be 1 because it's obvious, you can see it. And if it goes into the infinity, it will be going towards 0. So because of that, I can simply take the value of the function at the point t equals 0 as the calculated integral value. So when I take the Laplace transform of the Dirac delta function, I'm going to get a 1. Okay? This relationship is important for us, knowing the relationship. Then if I take the derivative of the Laplace function, because I can, as it's differentiable by definition, all the effort is done to make some discontinuity differentiable and define the derivative at that point. So for its derivative, I can write from 0 minus to infinity the derivative of the delta function times e to the minus st dt. And in this case, I'm going to get the integral as e to the minus st d sigma, delta t. So here, I just write it down, taking it into the, the dummy variable, using some kind of, substitution, and I end up with e to the minus st. And we know that if you take the integral of the e to the minus st, it will be the same, and by using this, we can get rid of the integral e to the minus st times delta t from 0 to infinity minus from 0 minus to infinity delta t times de to the minus st. So this definition will help us to further, simplify this thing. And I can write down a new, this computation will yield minus from 0 minus to the, infinity, minus s times delta t times e to the minus st dt. So I can represent this as s time, since s is constant from time domain point of view, as we have the t as our variable, s can be treated as a constant here, okay? We are taking the integration over time. And using this, I can represent it as s time Laplace transform of delta t, okay? And this will give us an s. Now, when we look at the Laplace transform of the derivative, when we do this, math using the, algebraic methods that we have learned in calculus classes, we end up with s. So if you look at this relationship, a time domain derivative has been transformed into a linear constant variable. It's constant from time point of view, but it's a variable in frequency domain. So we got rid of the integral, we got rid of the integrals and the differentials, but we end up with some, regular expression like s. This is where the true power of Laplace transform comes. And we use this a lot when we are dealing with circuits, especially AC circuits and, circuits that we would like to explore the time domain and frequency domain behavior. Now, the most generalized solution, like if you do the mathematical induction and do this over and over and over again, thanks to the e to the minus st, we end up with a regular relationship between the time domain and the frequency domain. If you take the nth derivative, if you take the Laplace transform of the nth derivative of the impulse function, then it's going to be, as you can see, s to the n. So basically, this is how we use Laplace transform to transform the integral differential equations into, linear algebraic equations. They can be nonlinear as well, depending on the, degree of the derivative. But at the end of the day, they are easier to solve, as dealing with or working with polynomials is much easier than dealing with differential equations if you compare the effort that you need to spend to solve it. From here, it's also possible to remember or define that the unit impulse function is the derivative of the unit step function. Now, if we go back to our unit step function, as you can see, if I take the derivative of this function, since all the constant portions except for a, where there is a transition in time occurs, will be 0, because this is constant, and if you take the derivative, it's going to be 0. And this is also a constant dc value. If you take the derivative, it will be 0. But at point A, we are going to get a pulse with an amplitude of k. Just a single line drawn in the positive y direction. This is very important to understand the time domain behavior of certain circuits, switching circuits. Okay. So functional transforms are easier to handle, like the functions that we will be dealing with are typically like delta function, the unit step function, e to the minus at kind of decreasing or decaying, diminishing, functions, and sinusoidals like cosine or sine. So all of them has, all of these functions have Laplace transform equivalents available. You can derive them to learn or as an exercise using your calculus skills, you can solve them and calculate these as an exercise. However, in most of the time, the important thing is understanding and knowing this equivalence. Like, okay, if I see a 1 in frequency domain, it will be corresponding to a delta t, which is a impulse function, unit impulse function in the time domain. If I see a 1 over s term in my equations in the frequency domain, it will be corresponding to an unit step function in time domain. And if there is a term like 1 over s plus a, it will be corresponding to the e to the minus at. So for us, in functional transforms, it's essential to learn about these pairs, okay, these transform pairs. You will be you will get used to it as you solve problems and use this in action. But do not get horrified by these integrals, because we are interested in the ends of these integrals. That is the input and the output of the integral, which is already calculated for us. So we will be basically using these relationships to make our journey to the frequency domain and then come back into the time domain. It's kind of being Doctor Who and going with the TARDIS kind of a thing. And Laplace transform enables us. Laplace will be our TARDIS to make our transitions from time domain to frequency domain, or vice versa. So for the sinusoidal case, for sine omega t, we will get omega over s square plus omega square. So these will be corresponding, functions, bilateral functions on the time domain and the frequency domain. We will be equating these. Other than that, we will also have this table basically, okay? Let us get rid of the integrals, which horrify students and people. Let us focus on the transform pairs. These functional transforms will help us solve certain cases of signals that we encounter in electrical engineering a lot. As you can see, we will have a ramp function, we have a damped sine or a damped cosine. In all cases, if you go with the basic definition of the Laplace transform and use your calculus skills, you end up with those Fs functions, okay, in the frequency domain. The good thing is when we do math in the Fs domain and find out a solution for a particular problem, then we can also jump into time domain back again to estimate the time domain behavior, which is very useful, because we are bypassing all the hardness or all the tedious tasks associated with the solving integral differential equations. And when we come to the, at the beginning we mentioned about the, functional and operational transforms. The operational transforms are also very useful, especially when we are dealing with circuit equations coming from node or mesh analysis, like the KCL and KVL, basically. The operational transforms, the properties of the operational transforms are also important for us, as we need to do the algebra with this in the frequency domain. We need to know the properties of it, okay? If we multiply a function in time domain by k, it means that in frequency domain, its Laplace transform will be multiplied by k. Okay, this is easy to remember as the effect is, symmetric. If you have multiple functions and if you have multiple function versus frequency domain representations, you can simply do basic addition or subtraction through them. And this is again easy to handle because all the separate transformations, Laplace transforms, can be combined, added, and subtracted correspondingly. Okay, these two are easier to understand. When we have a differentiation in the time domain, if we have uh, like if you take the first version of it, then using the definition of the Laplace transform, we see that we end up with the s to the 1 times the Laplace transform of it. So we end up with sfs minus the time domain value of the initial, which is basically sometimes it's 0 and sometimes it's defined by the question. But this is the initial condition, basically, initial value of the ft, basically. So if we, by mathematical induction, basically, we also see that if the nth derivative of the function ft is taken in time domain, and if you transform it into the frequency domain, then you are going to get a regular structure shown like this. So you are going to get s to the n fs minus s to the n minus 1 time domain value of the f0 um, minus s to the n minus 2 times df 0 divided by dt. Okay, and like this. So this is the generalized structure for the nth derivative. So for instance, for the second derivative, you are going to get s to the 2 fs minus s times f0 minus, since n is 2, this will be 1 df 0 at 0 dt. So it means that, for instance, if you take a look at the second derivative, we need to have a function which is differentiable at the point of 0. As long as it's differentiable, we can simply substitute the initial values and then solve it in the frequency domain. We can deal with it in the frequency domain. Now, the interesting thing is, as the degree of the differentiation operation increases, we are going to get polynomials here. Polynomials that can be factorized. And we are good at dealing with the polynomials, as they are much easier to handle when you compare it to integration or differentiation operators. So although it looks confusing, you will get used to it as we use it in solving questions or doing the math with the Laplace transform. It will become more meaningful. So if you have an integral, you can also take the Laplace transform of it. For instance, the integral of fx dx from 0 to phi, since it's the linear operator, like we can simply put this into the Laplace definition. Okay, as you can see, this is our function, and e to the minus st dt, this defines the Laplace transform. So if we make a variable substitution by defining u equals to integral from 0 to t fx dx, then du should be ft dt, right? And if I define the v as minus e to the minus st over s, I can also compute the dv as e to the minus st dt. And I can rewrite this as e to the minus st over s integral from 0 to t fx dx, defined in the boundaries like from 0 minus to infinity, plus integral from 0 to infinity e to the minus st over s ft dt. Now, This, as you can see, is the fs already. So we get 1 over s fs. So when we are taking the derivative, we get an s or s time, fs. And when we are taking the integration, we get the reciprocal, which makes sense because the differentiation and integration are, opposite operators to each other. So in the frequency domain, we obtain 1 over s times fs. So for the evaluation at the lower limit is 0, whereas the evaluation at the upper limit is also 0, because we are assuming that ft has a Laplace transform, because we are only dealing with functions that has Laplace transform basically. Because of that, we get these, 0, and the next term will be defined as 1 over s fs. And this is also a handy relationship. So as you can see, we can, whenever we do the transformation from time domain to frequency domain using operational Laplace transform, we end up with polynomial functions, which can be factorized and which can be handled very easily. And this will become very useful, especially when we are dealing with transfer functions. This forms a very, powerful tool to explore and understand the behavior of circuits. So we can have shifted functions, like if I have a function ft minus a, and if I multiply it with my unit step function t minus a, let's say, all of them are shifted and they're, multiplied. I can define this as an integral from 0 to infinity ut minus a times ft minus a times e to the minus st dt, which is the Laplace transform definition. Basically, I'm just substituting it. This would correspond, we know that this will correspond to an integral from a to infinity, because the function will start at a, because the unit function steps unit step function steps at t equals a, 0 other for t smaller than a. So we know it by heart. So the definition becomes from a to infinity ft minus a e to the minus st dt. Now, so for this, we can make an algebraic trick here. We can change the integration or substitute a different variable. If you let x equals t minus a, then if x equals 0, we know that t should be equal to a. When the x equals infinity, like x goes to infinity when t goes to infinity. From here we can also see that dx equals dt. Now, if I do that change again, I can redefine my function or integral as defined from 0 to infinity because of this property fx e to the minus s x plus a, okay, dx. And this looks very like the Laplace transform original definition. I just need an extra a here and s. So e to the minus sa is a constant, so I can move it out of the integration. And then the integration here is the definition of the Laplace transform, which corresponds to the fs. Okay, so if I have a shift in time, then this will be translated as e to the minus as times fs. So if I know the function and if I know this Laplace transform, then I can easily compute a more complicated version or shifted version of it in the frequency domain as well. It will be scaling with this e to the minus as. So if I have, like, how about if we multiply an ft with e to the minus at, which is a common scenario, especially we have seen this kind of behavior in second order RLC circuits, especially when the FT is sinusoidal, or even with DC, we will see this kind of behavior a lot in electrical engineering. So it's important. When you encounter a function like this in time domain, it will be translating into fs plus a. So if you need to take the Laplace transform of such function, you can directly substitute s plus a into frequency domain. Okay. So for cosine omega t, we have s divided by s square plus omega square. And when we have the Laplace transform of e to the minus at cosine omega t, it will be s plus a divided by s plus a square plus omega square. So the important or the common or popular functions, time domain functions that we encounter in circuits and their Laplace transform pairs are well defined. Knowing these relationships are important, although the concept can be a bit confusing from time domain to frequency domain, it will become more clear. But we have a very neat mathematical relation that will be enabling lots of easiness for solving the problems. We can also scale the variable. For instance, if I substitute at in place of t, then in the frequency domain, it will be acting on the opposite direction, like it will become a reciprocal prescaler to the function. So the Laplace transformation of f a t would be 1 over a times f times s over a. Okay, for a greater than 0. And for, let's say, for cosine t, we can simply do the math, and we will obtain s over s squared plus 1. And for instance, in cosine omega t, as you can see here, I can use this property. I just need to write down 1 over omega, and I need to substitute s over omega into the place of s here, as you can see. And if you just do some symbolic manipulation, then you end up with the s over s squared plus omega squared, which is the original relationship. So if you know the basic relationships and the properties, then you can use them to compute the Laplace transforms of other functions, even without taking the integral at all. Okay. So how do we, apply this into circuit analysis? So let us just, talk about an example that we have seen before. Going back into the RLC circuits, we have a parallel RLC circuit here, as you can see, and I have a DC current source, and a switch simply opens at time equals 0, so that the current IDC will be rushing into the RLC circuit. We are familiar with this, with the constitution of the differential equations for this particular circuit. Basically, you will write down a KCL at the single node of the circuit, and this is a constant, current. So it's a constant force, that is creating a sudden change in the dynamics, and the dynamics is defined as this. So I have a VT, the voltage, the node voltage, and VT over R defines the current through the resistor, and 1 over L integral from 0 to T Vx dx defines the current of the inductor, and the current of the capacitor is defined as C times dVt over dt, and their sum should be 0. So from there, I will obtain this equation. Now remember the relationships that we have seen previously. If I need to now go into the frequency domain, I need to transform my variables into the frequency domain variables. So Uh, First of all, variables will be capitalized, as you can see. The Vt will be Vs because we are in now frequency domain. And since r is constant, we will simply have Vs over r. And for the integral, we know that an integral operator will bring us a 1 over s, while the differential operator will bring us an s Vs minus the V0, which is the initial value of this node voltage. So I have to write it here. And since 1 over L here is constant, we will have 1 over L Vs over S, okay? And C times S Vs minus V 0 minus here. The V is the time domain value of it, okay? And that would be equal to the constant, function. And I'm modeling this circuit switching behavior with unit step functions. So I know that its Laplace transform will be 1 over s. See what happened. I had a second order differential equation here, basically, or integral differential equation. And suddenly I transformed it into the frequency domain. So I don't have to deal with all those complications or differential equation methods or tricks to handle this solution. Okay, so I end up, if you collect all the unknowns and the known values, Vs is what we are trying to compute basically. Okay, Vs times 1 over r plus 1 over Sl plus Sc equals to IDC over S. So from here, I'm assuming that we know the IDC as it's the input to the system. We can define Vs as IDC over C divided by S square plus 1 over RCS plus 1 over LC. Okay, and this, knowing this in the frequency domain, the solution of the Vs will be this. Now, once we obtain this solution, we need to go back into time domain because mostly it's easier to perceive as we are bounded with space and time. So we need to go back. How can we do it? We do it with the inverse transform. But in order to create the inverse transform, we need to manipulate this solution a bit, maybe factorize it into different, factors, and then use the basic relationships between time domain and the frequency domain for Laplace transform to estimate or write down the time domain solution. So basically, inverse transforms are a rational function of S. The function can be expressed in the form of a ratio of two polynomials in S, such that no non-integral powers of S appear in the polynomials. Okay. So Fs can be defined as ns over ds. As you can see, all the functions will typically, when we go into the frequency domain, solutions will be in the form of ratio of two polynomials. Okay, so in we will have a numerator and a denominator, ns over ds typically, and it will be formed. It will have some coefficients, kind of a power series sort of structure, and another one in the denominator. Now, for proper, rational function, we need to have m greater than n, and improper rational functions, m will be smaller than equal to n, but they can always be converted or reduced into a proper rational function by making the polynomial divisions as well. Okay. Typically, a proper rational function is expanded into a sum of partial functions. Okay. In order to have a proper rational function, the degree should be smaller than equal to the degree of the denominator should be smaller than equal to the denominator. Remember that. When I have this kind of ratio of polynomials, I can decompose them into sum of certain terms. Okay, As you can see, when I factorize, I can see that here in this particular example, for instance, s plus 6 divided by s times s plus 3 times s plus 1's square can be decomposed into um, terms like k1 over s, k2 over s plus 3, and k3 over s plus 1 square, and k4 divided by s plus 1. We can have multiple roots. Okay? As you can see, denominator has a degree of 4 because s plus 2 will have s square, and if we multiply it with s, it will be s cubed, and then s to the 4. So since we have 4 roots in the denominator part, we will have 4 different terms. And from here, we are going to get 2 distinct roots at s equals 0, because as you can see, they are doubled here when we, do the mathematical expansion. We are going to get a root at s equals minus 3, and we will get multiple roots at s equals minus 1. So if we are basically following a divide and conquer approach here. Okay, this looks complicated, so we say that it must be composed. We can factorize the denominator in such a way that these terms will be combined somehow. We don't know these coefficients k1, k2, k3, but they are solvable. And each term can be equated to a Laplace transform, and then we can estimate the time domain function from there. Like as you can see, we have 1 over s plus 3, and this kind of portions are easier to handle when you compare it to the whole. So if I take the inverse Laplace transform, it will be k1 plus k2 times e to the minus 3t, because this is e to the minus alpha t, and alpha is like 3 here, as you can see. And then the third term will be k3 times t times e to the minus t, the ramp function, and k4 times e to the minus t u times ut, like the unit function, as the Laplace is defined for t greater than 0. We multiply it with the unit step function to make it mathematically compliant. But eventually what we have done is we go into frequency domain, we computed something, and then we decompose it, we factorize it. And then for each term, we computed the time domain equivalent by taking the inverse Laplace transform. So it's essential to have an understanding or knowledge of the time domain function and the frequency domain transform. If you see the transform, you can estimate the time domain function, or if you have the time domain function, you can transform it into the frequency domain to do solving. So this is how actually we simplify the solution of integral differential equations. We first take the Laplace transforms to transfer all these equations into frequency domain, do all the kung fu and fight there to solve, and then factorize the solution. Then, using the basic knowledge or the matching of these terms in frequency domain back into time domain using the inverse Laplace transform, we construct our solution, so that we avoided all the traditional methods of differential equations and solving them. So the identity sign is used here to emphasize the expansion of a rational function into a sum of partial fractions establishes the identical equation. Okay, this is why we use the identity sign. So both sides of the equation must be the same for all values of the complex variable s. Also, the identity relationship must hold when both sides are subjected to the same mathematical operation. All that remains is to establish a technique for determining the coefficients. Now, the coefficients are currently unknown. We can make our journey from time domain to frequency domain and frequency domain to time domain, we have established all our, we have charted our map basically. We can move, navigate, but still we need to identify those coefficients. Okay. Now, this is typically four general forms this problem can, basically take. The roots of the DS are either real and distinct. They could be complex and distinct. They could be real and repeated, or complex and repeated. So four different cases can be treated properly, and then using that we can estimate the coefficients and solve them. We need to make sure that the rational function is a proper one. Okay, so the degree of the nominator should be always smaller than the degree of the denominator, so that we can apply the aforementioned techniques. Okay, so let us take a look at an example to, show how it works in practice. So we have, let us assume that we did some, number crunching in the frequency domain, and we end up with an fs equals 96 times s plus 5 times s plus 12 divided by s times s plus 8 times s plus 6. So I check that the degree of the denominator is 2 and the degree of the denominator is 3. So I'm good to go. Then I speculate that looking at the denominator, I can decompose this into three different fractions in such a way that this function will be a combination of those. I don't know the k values, but I can write k1 over s as I have it as a factor in the denominator, and k2 over s plus 8, and then k3 over s plus 6. Now, in order to find the k1, we can simply multiply the both sides by the s, and then evaluate the both sides at s equals to 0. Then the k1 will be all alone, and the rest of k2 and k3 will be destroyed because s is 0. This is a nice trick to obtain the k1. If I do the math here, as you can see, I just, multiplied both sides with s, so I got rid of this s. Then I just substituted 0 into the left-hand side and the right-hand side at the same time. So I get rid of this term, also this term, and if you substitute 0, then if you do the, number crunching here, you end up with k1 equals to 120. As you can see, we have directly found the k1. Great. Then with a similar approach, I can simply multiply all the sides with, for instance, s plus 8, and I can provide s equals to minus 8. And then by using this approach, I can compute all these coefficients, and we can get k2 as minus 72 and k3 as 48. So at the end of the day, this expression is decomposed into this one, and we have determined the coefficients. So now I can go back into time domain because I have divided my problem. It's time to conquer, right? So if I take the inverse Laplace transform for each term, I go to my chart that shows me the function and Laplace transform pairs, and from there, using the properties, I will go into time domain. And in time domain, we get 120 plus 48 times e to the minus 60 minus 7t times e to the minus 8t times ut as our time domain solution. So this is how we apply it in practice. If you are in the frequency domain and if you have some solution, then the properties of the Laplace transform and the inverse transform are used to constitute the solution, to find the solution in the time domain without dealing with all the differential equation hardness or stuff. In the case of distinct complex roots, when we have uh, real solutions basically, or distinct, it could be also complex, doesn't really matter. The important thing is that they are not overlapping. So in this particular example, for instance, when we have 100 times s plus 3 divided by s plus 6 times s squared plus 6s plus 25 as an example, we can easily decompose it. We can simply find the roots of this, okay, whether it's complex or real, but it will have two distinct roots which are complex conjugates of each other. So I can still decompose this or factorize this into some of some expressions. Then we can simply use the technique we have learned previously to find the coefficients as well. We multiply with, for instance, s plus 6, then we substitute minus 6 into it to isolate k1, get rid of the others, and compute the k1 and k2 and k3 in a very similar manner. Okay, you just need to multiply it and then give the value that zeroize the rest of it. So you isolate and pick or calculate your coefficients. So as you can see, for K2 we have 6 minus J8, and thankfully you only need to know the half of it because the other half will be the conjugate of it. So it's easy to predict or write down, and you can also represent it as a phasor notation, a polar form. Or in yeah, it's easier to it's a compact representation. So our solution in the frequency domain can be decomposed into a ratio of numbers like this. And from here again, we can use the basic properties of inverse Laplace transform to estimate its time domain response of this frequency domain representation. If you do the math, we end up with minus 12 e to the minus 60 plus 10 e to the minus j 53.13 degrees and times e to the minus 3 minus 4j times t plus 10 times e to the j 53.13 degrees times e to the minus 3 plus j 4 times t times unit step function ut. And as you can see, we know that using the Euler's relationship, we can further simplify this term as well. So if we, when you have distinct complex roots, like the factors will be in the form of s plus alpha minus jb times s plus alpha plus jb. So we will always have this kind of structure when especially we have complex roots. They will be complex conjugates, okay? So when we are doing our inverse Laplace transform, we can make use of this. So the coefficients of these terms will also be conjugates, okay? If you look at the solution here in the previous example, as you can see, the coefficients are conjugates of each other. This is a very useful thing because we only need to solve the half of the coefficients, okay? Once I know K2, I also know K3. I don't need to do the math. That's very useful. So this is what it tells us here. Like if you have these kind of pairs, then when you are taking the inverse Laplace transform of it, you are going to end up with something like 2 times the absolute value of k e to the minus alpha t times cosine beta t plus some theta. That comes from the phasor angle. So if we simply substitute this using this property, then we can rewrite our solution as minus 12 e to the minus 60 plus 20 times e to the minus 3t times cosine 40 minus 53.13 degrees times the unit step function. So this is how this could be further simplified. Um, so these are the basic techniques that we can apply during computation of the inverse transform of the Laplace. Um, when we have another case is the repeated real roots case. So when, for instance, in this example, when we have something like 100 times s plus 25 divided by s times s plus 5 to the 3, we can, again, since we have a repeated root at s equals minus 5, as you can see here, I'm going to write it down as a composition of other terms as well, like k1 over s, it's obvious here, but k2 over s plus 5 to the third degree, and k3 divided by s plus 5 to the 2, and plus k4 divided by s plus 5. Okay, so we go down by decreasing the exponent. Now we, for instance, k1 is easily computed as you multiply both sides with s and substitute 0, you got the k1. For k2, for instance, we need to multiply both sides by s plus 5 to the 3. Then we have to compute the value of the expression at s equals to minus 5. The same philosophy is applied here. So for instance, if we do the math, 100 times s plus 25 divided by s at s equals minus 5 equals to k1 times s plus 5 to the 3 divided by s at s equals minus 5 plus k2 plus k3 times s plus 5 at s equals minus 5 plus k4 times s plus 5 to the 2 at s equals minus 5. So if when we substitute these values, we are going to get k2 as minus 400, for instance. Thankfully, most of the terms are zeroized, so we end up with the k2. In order to find k3, we must multiply both sides by s plus 5 cube. So we just continue like this in a periodic, fashion. Basically, for k3, we have to, we end up with this kind of relationship, as you can see, the expression. Then we take the differential of both sides with respect to s, and we still can evaluate at s equals minus 5. Because since we are treating to both sides, the equality will be held. We basically get rid of the excessive s terms here. So taking the derivative on the both sides, d over ds k1 times s plus 5 to the 3 over s plus d over ds times k2s at s, all of them are computed as s equals minus 5. So if you do this math, we will end up and find k equals to minus 100. So when we put s equals minus 5, most of these terms will be zeroized, and we end up with the k3. And to find the k4, we now multiply both sides by s plus 5 to the cube. Then we differentiate both sides twice with respect to the s. Basically, if you have n to the n, you have to differentiate until n minus 1 and evaluate the both sides at s equals minus 5. If you do this math, you end up with a k4 of minus 20. And so we now have all the coefficients established. We can use the inverse Laplace transform relationship to compute back in time and go back in time and represent the solution in time domain. So how do we do this? We basically write down our coefficients, computed coefficients, then using the basic relationships, I go into time domain. Each term is transformed into time domain correspondingly, as you can see, and we end up with 20 minus 200t square times e to the minus 5t minus 100t times e to the minus 5t minus 20 times e to the minus 5t times unit step function ut. So this, although looks complicated, it's doable because it's all about the polynomials, and taking the derivative of a polynomial is also very easy and it can be done. And since we typically try to compute the values that zeroize other terms, it's gonna be pretty handy and useful when we have repeat, real roots. If we have repeated complex roots, the problem will be handled in a very similar manner. So um, it will be again the same approach. The only difference will be that the algebra will be incorporating complex numbers, which might be prone to errors, especially when you are doing it by hand. Complex roots always appear in conjugate pairs. That's an advantage in this case. And coefficients associated with a conjugate pair are also conjugates. This is an important principle that you should keep in your minds to make your life easy. So half of the case needs to be evaluated in this particular case. For instance, if we have a function like fs equals 768 divided by s squared plus 6s plus 25 to the power of 2, we can simply write down it as 786 divided by s plus 3 minus j times 4 to the 2 and multiplied with s plus 3 plus j times 4 to the 2. And we can decompose this into four-term, fractions. And within that fractions, we will have coefficients like k1, k2, and k1 star and k2 star. Now, looking at this, I just need to compute two things, k1 and k2. Once I know them, I can solve it all. Now, in order to solve k1, we isolate it by multiplying with s plus 3 plus j times 4, and then substitute minus 3 plus j4 to the s, and then the k1 will be equal to minus 12, as you can see here. So the conjugate of the k1 will be again minus 12 because it's real, we don't have any imaginary parts. So k1 star and k1 are minus 12. For the k2, we have to take the first derivative and then compute this 768 divided by s plus 3 plus j times 4 to the square at the point s equals minus 3 plus j times 4. So that will yield numerically minus j times 3. And it can be represented as a phasor and 3 times with a degree of minus 90. Then k2 will be j times 3. So knowing this, I can write down my fs with the coefficients like this, okay? Minus 12 divided by s plus 3 minus j times 4 square plus minus 12 divided by s plus 3 plus j times 4 square plus the 3j divided by s plus 3 plus s plus 3 minus j times 4 plus the minus 3j divided by s plus 3 plus j4. So as you can see, we have the minus 3j and plus 3j coming here and there. So these terms can be reworked to transform back into time domain using the inverse Laplace transform as minus 24 times t times e to the minus 3t cosine 4t plus 6 times e to the minus 3t times cosine 40 minus 90 degrees multiplied with unit step function. Now, if we have multiple real roots, then we are going to get something like k divided by s plus a to the r, and the Laplace transform of this will be k times t to the r minus 1 times e to the minus at divided by the factorial of r minus 1 times ut. Okay. So basically, we can use this for cases when we encounter this kind of term. When we have multiple complex roots, like k divided by s plus alpha minus j times beta to the r, plus k conjugate divided by s plus alpha plus j times beta to the power of r, the inverse Laplace transform of such expression will be 2 times the absolute value of k times t to the r minus 1 divided by the factorial of r minus 1 times e to the minus alpha t times cosine beta t plus theta times the unit step function. Now, these things could be harder to, remember. They are not as simple expressions as the ones that we have seen before, but they are useful. When you encounter such a complicated scenario, you can easily consult to an Laplace transform table, which would help you to find your path towards the solution. When we talked about the fact that we can have proper or improper rational functions. When we have an improper rational function in which the degree of the numerator is greater than the degree of the denominator, we just need to transform this into a proper rational function by dividing two polynomials, like by dividing the numerator with denominator, and we will be doing polynomial arithmetic basically. And in that case, our expression can be rewritten. Here we have an fs equals to s to 4 plus 13s to the 3 plus 66 times s to the 2 plus 200s plus 300 divided by s squared plus 9s plus 20. Since the degree of the denominator is larger than the degree of the numerator is larger than the degree of the denominator, I can make a proper division, because if you do, you can easily factorize and you can get or rewrite this thing as this. Okay. Now we now have a proper rational function, which we can decompose into and compute the coefficients with the methods that we have learned before. It will have some distinct roots, and using the basic relationship in those scenarios, we can rewrite this portion as minus 20 over s plus 4 plus 50 divided by s plus 5. And for the, for this part, we can also see that the s square comes typically from the second degree derivative of the delta function, and the s comes from the first derivative, and 10 is basically 10 times the delta t. So I can write down by doing again the inverse Laplace transformation from the frequency domain, and I end up with this representation. Okay. So this is how we handle the improper rational function solutions in frequency domain, and we transform them into time domain using the inverse Laplace transform. So as a summary, we have learned about Laplace transform. Basically, it was like some calculus class, because we need to first establish the mathematical foundations, and we need to understand the operational properties of it. Then we will be learning how we apply the Laplace transform in circuit analysis. Knowing the transformation pairs, reduces the computation time a lot. You typically can easily remember the easy and basic ones. And if you encounter more complicated ones, you can always consult to a source of Laplace transforms to guide you in finding the solution. As mentioned before at the beginning of the course, Laplace transform is very powerful. Although it sounds weird at the beginning or it may look complicated, it's much easier when you compare it to the time domain solution of the integral differential equations. We basically bypass the methods in the time domain by migrating or shifting into the frequency domain and then doing all the dirty job of finding the solution there and then applying the inverse Laplace transform to come back into time domain. And in order to simplify things, we also have some, relationships that we can use to our advantage as we have learned. And through some examples, we try to represent how these properties are used to find out the time domain uh, representations. In order to have a good understanding of this, it's essential that you solve questions, you try to solve questions on your own with the guidance of the book and try to get a hold of it. Once you have understand the basics, then it will be much easier to apply it, especially when we are dealing with circuits. Uh, this will be the basis. So it's essential and important that you understand and work on this so that all in your future classes and all other places, we will be using the concepts and the properties developed. So the best thing is learning by doing, and you will learn more about it in future courses. Thank you for your attendance. See you next time.